I am David, Assistant Professor, Department of Mechanical Engineering, Rohini College of Engineering and Technology. I am going to teach you the subject additive manufacturing. So it is from second unit. Module 3 is optimization. So optimization, as with any design, optimizing the part performance is crucial. Design optimization can be done in a number of ways, such as size optimization and topology optimization. Size optimization is often done in parametric models to fine-tune dimensions and is a relatively well-established field with many commercial software options. Topology optimization. Methods of topology optimization started being developed around the same time as additive manufacturing due to the organic and often quite complex shapes produced through topology optimization. The usefulness of the approach for products intended for traditional manufacturing methods has been limited, but the number of feasible applications has grown. Topology optimization can largely be divided into 8 steps, that is, define design space, define non-design space, define boundary conditions, define constraints and objectives, define optimization settings, then solve, interpret the results, then validate. First step is define design space. The design space is a volume within which topology optimization algorithm can redistribute material. In order to give optimization algorithm the best possible starting point, the design space should be as large as possible. Second one, define non-design space as surfaces where the product interfaces with other parts such as fasteners or bearings should remain unaltered by the optimization. This should be marked as non-design space. Define boundary conditions. As with any analysis, the boundary conditions need to be chosen with care. They should, as closely as possible, represent the real loading of the part. It is easy to, for instance, and a constraint that will take up forces in all directions, whereas in reality, the support might only take up forces in compression. Define constraints and objectives. There are a number of possible constraints and objectives that may be set up for topology optimization. The most commonly available objectives include minimizing the compliance and minimizing the mass. These objectives will obviously not generate useful design by themselves and need to be coupled to constraints. For instance, minimizing the compliance is often linked to a constraint on the percentage of the volume that should be retained. Next step is define optimization settings. Most software will allow the user to define parameters such as mesh density and minimum feature size. The mesh size affects the level of detail that the resulting geometry will have, and of course, the computation time. In theory, the finer the mesh, the most optimal the results. Then next step is solve. The solution time will go up with the number of load cases and mesh density. While reducing the number of load cases to reduce the computational time may be tempting, doing so will yield results that are not useful. Reducing the number of elements, on the other hand, will not typically affect the overall distribution of the material, but will only have local effects. For initial optimization of the concepts, it is therefore recommended to adjust the number of elements. Interpret the results. The results from the topology optimization is most commonly in the form of a mesh-based model. Although there are a number of experimental methods to aim to make the process for optimization to manufacturing more streamlined. Thank you.